Okay, let's dive in. Time series forecasting. It's just so fundamental, isn't it? Predicting the future based on the past.
Absolutely. Think finance, climate, energy demand. It's everywhere.
And usually, these powerful models, they spit out just one number, right? A point
That's
forecast.
the standard, yeah.
Yeah.
A single value for each future time step.
Like my weather app saying 22 degrees Celsius, exactly. But, you always wonder, how sure are they? What's the actual range?
Exactly that. That's the whole issue of predictive uncertainty. How much can we really trust that single number?
Mm.
We've seen Mamba models do great things for point forecasts, but they give you that one value. And when you hear about, say, an 8% mean error in electricity forecasts or maybe 18% in traffic,
Yeah.
you're left wondering.
Yeah, is that just the model being a bit off, or is the data itself naturally spread out like that?
Precisely. You need to disentangle model inaccuracy from inherent data variability.
You need the bigger picture, not just the best guess.
Right. And that leads us straight into this really interesting paper we looked at. It's called Mamba Time Series Forecasting with Uncertainty Quantification. Came from Pessoa and some colleagues at Arizona State University.
Okay.
And their whole goal, their mission, was basically to bolt on this uncertainty quantification piece onto Mamba forecasts to give you that reliability info.
Okay, awesome. So for everyone listening, that's our mission today. Let's unpack this paper, dig into the sources you shared, and really get our heads around this Mamba-ProbTSF framework they developed. What makes it tick, and what does it mean for getting forecasts we can actually, rely on?
So the real core innovation here, academically speaking, is how they structured the model. It's a fundamental shift. Instead of just one big network doing everything,
Yeah.
they use two separate neural networks working together, but each with its own job. That's the key to how they quantify the uncertainty.
Two networks. Okay, that sounds interesting. What's the first one doing?
So the first one, they call it the e-network mu. For the mean its job is to predict the average future path, the trajectory.
Ah, so that's basically giving you the traditional point forecast, the most likely outcome.
Exactly. And they typically use the S-Mamba architecture for this, which we know is pretty good for sequences. They also mention pre-training this network first,
Why pre-train it?
just to get a stable starting point, apparently. Get the mean prediction reasonably good before you start worrying about the uncertainty part. Makes sense for stability.
Okay, got it. Network 1 predicts the center line. What about network 2?
Right, network 2, the said network. For sigma, this one is dedicated purely to estimating the uncertainty. It models the variance for each step in the future.
Okay, so it's telling us how spread out things might be around that center line.
Precisely. And here's a really interesting detail from the supplemental materials, actually. You might think, just use S-Mamba for both networks, right?
Yeah, seems logical.
But it turns out, for this sigma network, when they tried S-Mamba on the real-world data electricity, traffic it tended to seriously overestimate the uncertainty.
Really, the architecture that's good for the main pattern isn't good for the pattern of the spread.
Kind of surprising, right? On synthetic data, where the noise was perfectly controlled, Gaussian noise, S-Mamba for sigma was fine. But for the messiness of real data,
Yeah.
a simpler approach actually worked better. Just a standard fully connected network, but with a soft plus activation function.
Soft plus, why that specific activation?
Well, soft plus guarantees the output is always positive.
Yeah.
And variance has to be positive, right? You can't have negative spread. So that choice keeps the math sound when you use that variance estimate later.
Yeah.
It's a subtle but crucial detail.
Okay, so network 1, S-Mamba, gives the mean. Network 2, simpler, fully connected with soft plus, gives the variance, telling us the width of the uncertainty.
You've got it. And this leads to the next sort of key academic pillar here, the underlying assumption about the shape of that uncertainty. The framework assumes it's Gaussian, a normal distribution.
The classic bell curve. Why assume Gaussian? Real data isn't always perfectly bell-shaped, is it?
No, it often isn't. But there are solid reasons for this choice. First, Gaussian noise is a common model for random errors in lots of scientific processes. Things just add up.
Okay.
And second, there's a deeper principle. Maximum entropy. If all you're predicting is the mean and the variance, which is exactly what our two networks give us, the Gaussian distribution is the one that makes the fewest extra assumptions. It's the least biased choice given only that information.
I see. So it's a principled starting point, even if reality is a bit messier. It's mathematically convenient and theoretically sound, given what the model outputs.
Exactly. It provides a trackable way to build the probabilistic model. So you've got these two networks, one predicting the mean, one predicting the variance under this Gaussian assumption. The next big question is, how do you train them together effectively?
Right. You want them to produce forecasts that are, probabilistically consistent.
Precisely. And the way they do this is by minimizing a specific loss function, the negative log likelihood of that Gaussian distribution.
Negative log likelihood. Okay, I've heard that term. How does that actually work in training?
Well, think about what likelihood means. It's the probability of seeing your actual data points, given the model's parameters. So maximizing the likelihood means finding the parameters are predicted mean and variance that make the observed data most probable. Minimizing the negative log likelihood is mathematically the same thing.
Okay.
And the beauty of using this loss function is that it inherently considers both the mean and the variance. It doesn't just try to get the mean prediction close to the actual value. It also looks at the predicted variance. If the actual data point is far from the predicted mean, the loss is high, unless the predicted variance was also large for that point.
So it encourages the model to predict high uncertainty, large variance, when its mean prediction is likely to be off or when the data is just naturally very spread out.
Exactly. And conversely, if the mean prediction is good and the data is tightly clustered, it encourages a smaller variance prediction. It naturally optimizes both networks together for that probabilistic consistency we talked about.
That's clever. It's not just about accuracy, but about accurately representing the confidence in that accuracy.
Precisely. And remember, they do that pre-initialization step for the mean network first, just using a standard error loss, like mean squared error.
Right, to get it in the ballpark before bringing in the probabilistic part.
Yeah, gives it a good head start. And of course, for practical training on large time series data sets, they use mini-batching.
Makes sense. Got to handle that data volume efficiently. Okay, so the model is trained, it's spitting out means and variances. How do they actually check if the uncertainty part is any good? Measuring the mean error is straightforward, but how do you measure the quality of the variance prediction?
Great question. That's where they bring in a really crucial diagnostic tool, standard practice in probabilistic forecasting, analyzing the standardized residuals.
Standardized residuals. Okay, break that down.
It's actually quite intuitive. For every point in your forecast, you look at the actual observed value.
Okay.
You subtract the mean value that your Modo network predicted for that point.
Right, the error.
Then you divide that error by the standard deviation that your network predicted for that same point. Remember, standard deviation is just the square root of the variance.
So it's actual value predicted mean, predicted standard deviation.
Exactly. You're essentially asking, how many predicted standard deviations away was the actual outcome from my mean forecast?
Okay, I get the calculation. What does it tell you?
Here's the key insight.
Yeah.
If your model is working perfectly, capturing the dynamics correctly, and that Gaussian assumption holds true, then if you calculate these standardized residuals for all the points in your test set and look at their distribution, that distribution should look like a standard normal distribution.
Meaning a bell curve centered perfectly at 0 with a variance of exactly 1.
Precisely. A mean of 0 tells you your mean forecast is unbiased on average. A variance of 1 tells you that your predicted standard deviation was, on average, the right size. Not consistently too wide, not consistently too narrow.
Wow, okay. That's a neat way to check both aspects.
It is. And they use two main metrics based on this.
Go on.
First, they literally calculate the variance of the standardized residuals. Ideally, this number should be 1. If it's way bigger than 1, the model's under-predicting the uncertainty. If it's less than 1, it's over-predicting.
Simple enough. What's the second metric?
The second is the Kullback-Leibler divergence, or KL divergence.
KL divergence sounds fancy.
It's a concept from information theory. Basically, it measures how much one probability distribution differs from another. In this case, they measure the KL divergence between the actual distribution of the standardized residuals they got from the model and that ideal standard normal distribution.
So it quantifies how far the shape of the residuals distribution is from the target bell curve.
Exactly. Lower KL divergence is better. 0 means a perfect match. It gives you a single number, summarizing how well the model captured the overall probabilistic structure, assuming that Gaussian target.
Got it. So variance of residuals close to 1, KL divergence close to 0, those are the targets for a well-calibrated probabilistic forecast. All right, let's get to the results. How did Mamba-ProbTSF actually do when they ran it on the data from the sources? Let's start with the synthetic datasets, the ones where they knew the rules.
Yeah, they tested it on data generated from sons of sine waves plus known Gaussian noise, and also a nonlinear system called the Van der Pol oscillator. again with added Gaussian noise.
So basically, data designed to perfectly fit the model's assumptions deterministic process plus Gaussian noise.
Exactly. And on these, the performance was, well, frankly remarkable. Almost perfect.
Really? Give us the numbers.
For the science data set, the KL divergence was tiny, something like 10 to the minus 3. And the variance of the standardized residuals was basically spot on 1.
Wow.
For the Van der Pol oscillator, it was even slightly better. KL divergence down around 10 to the minus 4, variance again right near 1.
Okay, that's incredibly close to the ideal targets. It really validates the whole dual network approach and the training method, at least when the data behaves exactly as the model assumes.
Absolutely. It shows the framework is theoretically sound and works beautifully under those ideal conditions.
But of course, the real world isn't usually that clean. What happened with the actual data, electricity usage, traffic flow, that's usually messier.
Right. And on those real-world data sets, the performance was still definitely good and practically very useful, but the metrics weren't quite as perfect as with the synthetic data, which, you'd expect.
How far off were they?
The KL divergence was higher, maybe around 10 to the minus 1 for both electricity and traffic. Still pretty low, but not near 0. And the variance of the residuals, for electricity, it stayed reasonably close, below 1.5 mostly. For traffic, though, it showed bigger deviations, larger variance spikes, especially when there were extreme events like, sudden major congestion.
So the residuals weren't perfectly standard normal in the real world?
No, not perfectly.
Right.
Real-world fluctuations often have fatter tails or aren't perfectly symmetric like Gaussian. But here's the interesting practical takeaway the sources highlighted. The model tended to produce conservative uncertainty estimates.
Conservative, meaning the predicted uncertainty bands were maybe a little wider than strictly necessary.
Yeah, exactly. They looked at coverage probabilities, what percentage of actual data points fell within the predicted 1 standard deviation, 1 sigma, or 2 standard deviation, 2 sigma bands. For electricity, about 73% of points fell within the 1 sigma band, where a perfect Gaussian would have 68%. And 93% fell within 2 sigma, versus 95% for Gaussian. For traffic, it was even more conservative, 84% coverage at 1 sigma, 96% at 2 sigma.
So it's maybe overestimating the uncertainty slightly, especially in that central region. That actually sounds potentially useful in practice, right? Better to be slightly cautious.
It often is, yeah. Especially in areas like energy grid management or traffic control, where underestimating potential swings could be costly or dangerous. This slight conservatism, while not perfectly statistically calibrated, can be a desirable feature for risk-averse decision-making.
Did they see any impact on the basic forecast accuracy, the mean prediction?
Interestingly, yes, a small improvement for electricity. The mean absolute error dropped slightly, maybe from around 213 watt-hours to 209.
Yeah.
It suggests that maybe the process of learning the uncertainty structure also helped refine the mean prediction a little bit.
Okay, so performs well on synthetic, gives useful, slightly conservative uncertainty on real data. But didn't you mention there was a case where it fundamentally failed? That sounds really important to understand.
Yes, absolutely critical finding. And it tells us something profound, not just about this specific model, but about the whole class of models it belongs to, state space models, or SSMs, which Mamba is based on.
Okay.
The failure occurred when they tested it on synthetic data generated by Brownian motion.
Brownian motion, like pure random walk, where each step is just random noise added to the last position.
Exactly. It's a process where the randomness isn't just added noise on top of a smooth path. The randomness is the path. It accumulates over time. The key thing is its variance grows linearly with time. The uncertainty inherently increases the further out you forecast.
And SSMs like Mamba couldn't handle that. Why not?
This is the core academic insight here. SSMs are fundamentally designed, architecturally, to infer some kind of underlying latent deterministic process. They assume there's a hidden, smooth system evolving according to some rules, like a differential equation, and maybe there's noise added on top.
Ah, but Brownian motion doesn't have an underlying smooth deterministic process. The randomness is intrinsic.
Precisely. The model's core assumption about how time series work, find the hidden deterministic path, completely breaks down when faced with a process that is purely stochastic accumulation.
So the architecture itself is mismatched to that type of data.
Exactly. It struggled badly to capture that characteristic growing variance of Brownian motion. The sources showed the standardized residuals were way off from a standard normal KL divergence close to 1, variance spiking up towards 5. It's not just a small error. It highlights a fundamental limitation of the SSM framework when dealing with purely stochastic accumulative dynamics. That's a really significant finding about the applicability boundaries of these models. So yeah, summarizing those limitations. The Gaussian assumption, while practical, isn't always perfect for real data, leading to slightly imperfect residual distributions, though the resulting conservative estimates are often useful.
Right.
But the bigger takeaway is this fundamental mismatch between the SSM architecture's assumption of latent deterministic dynamics and processes that are purely driven by stochastic accumulation, like Brownian motion.
And did the authors suggest ways forward, how to potentially overcome these limitations?
They did.
Yeah.
They pointed towards exploring hybrid architectures, maybe combining SSMs with other types of models that are specifically better at handling stochastic processes.
Like mixing and matching.
Sort of. Or integrating more advanced probabilistic neural networks. They mentioned things like normalizing flows, which are designed to learn much more complex non-Gaussian probability distributions directly. That could potentially relax the strict Gaussian assumption and handle weirder data shapes better.
Interesting. So pushing the boundaries on both the core dynamics modeling and the flexibility of the probability distributions. Okay, so wrapping this up, this deep dive really shows Mamba-ProbTSF as a pretty sophisticated and academically solid way to approach uncertainty, using that dual network structure based on Mamba, trained with that specific negative log likelihood. It gives you not just the forecast, but a structured way to think about its reliability.
Absolutely. It's a clear step forward for getting probabilistic forecasts from these powerful sequence models. It worked exceptionally well when the data fits its assumptions, like on that synthetic data. And importantly, even on the messier real-world stuff, it provides useful, if slightly conservative, uncertainty estimates. But perhaps just as valuable is how this research clearly identified that fundamental boundary condition for SSMs.
The Brownian motion problem.
Right. Understanding when and why a model architecture might struggle because of its core assumptions, that's crucial scientific progress. It points directly to where future research needs to go.
So for you listening, you've now got a much deeper sense of this specific technique, Mamba-ProbTSF, how it works, its strengths, the Gaussian assumption, the training, the evaluation metrics like standardized residuals and KL divergence, and its key limitations tied to the underlying SSM structure.
It really moves beyond just, here's the prediction, to something much richer. Here's the likely prediction, here's a range we expect around it, and here's a measure of our confidence in that range derived from a principled probabilistic model.
And thinking about that limitation, that core assumption mismatch with Brownian motion, it really makes you consider, doesn't it? It highlights how understanding the implicit assumptions baked into any model's architecture, like the assumption of a latent deterministic process in SSMs, is maybe just as important as looking at its performance scores on some benchmark.
Definitely food for thought.
Yeah. What other models that we use all the time might have these kinds of built-in assumptions that limit where they can be reliably applied, perhaps in ways we haven't fully recognized yet? Something to ponder as you encounter forecasts, or even build them in your own work, or just out of curiosity.